Welcome to our lesson on the Doppler effect. The Doppler effect is a fascinating phenomenon that occurs in our everyday lives. You've probably heard it before, even if you didn't know what it was called. The Doppler effect is the change in frequency or wavelength of a wave, such as sound or light, as observed by someone who is moving relative to the source of the wave. It's important to understand that what causes this change is the relative motion between the source of the waves and the observer. Let's visualize this with sound waves. When a sound source is stationary, it emits waves uniformly in all directions. These waves travel outward as concentric circles with a consistent wavelength and frequency. However, when the source moves toward an observer, the waves in front of the source get compressed. This results in a shorter wavelength and a higher frequency as perceived by the observer. Conversely, when the source moves away from an observer, the waves behind the source get stretched out. This results in a longer wavelength and a lower frequency. Let's see a common real-world example of the Doppler effect: an ambulance siren. As an ambulance approaches you, its siren sounds higher-pitched because the sound waves are compressed, resulting in a higher frequency. As it passes by and moves away from you, the siren sounds lower-pitched because the sound waves are stretched out, resulting in a lower frequency. This shift in frequency is called the Doppler shift. The Doppler effect isn't just limited to sound waves. It also applies to light waves in astronomy. When a star or galaxy is moving away from Earth, the light waves get stretched out, shifting toward the red end of the spectrum. This is called redshift. Conversely, when a star or galaxy is moving toward Earth, the light waves get compressed, shifting toward the blue end of the spectrum. This is called blue shift. The Doppler effect has been incredibly important in astronomy. Edwin Hubble used redshift measurements to discover that the universe is expanding. Now, let's look at the formula for the Doppler effect, specifically for sound waves. The observed frequency f prime equals the actual frequency f multiplied by the fraction v plus v sub o divided by v minus v sub s, where v is the speed of sound in the medium, v sub o is the speed of the observer toward the source, and v sub s is the speed of the source toward the observer. Let's break down these variables. F prime is the observed frequency. F is the actual frequency emitted by the source. V is the speed of sound in the medium. V sub O is the observer's speed, positive when moving toward the source. V sub S is the source's speed, positive when moving toward the observer. The signs of V sub O and V sub S are crucial. They're positive when moving toward each other and negative when moving away. Let's work through an example to see how the formula works in practice. Imagine an ambulance with a siren frequency of 500 Hz, moving at 20 meters per second toward a stationary observer. The speed of sound in air is 343 meters per second. Let's calculate the frequency heard by the observer. We plug these values into our formula. F prime equals 500 Hz times the quantity 343 plus 0, divided by 343 minus 20. Simplifying, we get F prime equals 500 Hz times 343 divided by 323, which equals approximately 531 Hz. So the observer hears a higher frequency of about 531 Hz instead of the actual 500 Hz. This matches our earlier observation that an approaching source produces a higher frequency sound. Let's summarize what we've learned about the Doppler effect. When a source is approaching an observer, the observed frequency is higher and the wavelength is shorter. When a source is receding from an observer, the observed frequency is lower and the wavelength is longer. The Doppler effect has many important applications. In medicine, it's used in ultrasound imaging to measure blood flow. In law enforcement, it's used in radar guns to measure vehicle speeds. In astronomy, it helps measure the speed and direction of stars and galaxies. In weather forecasting, Doppler radar detects the movement of precipitation. The Doppler effect is a fundamental principle in physics that helps us understand how waves behave when there's relative motion between the source and the observer. It's a beautiful example of how the mathematics of wave propagation connects to everyday experiences, like the changing pitch of a passing ambulance siren.